There is a difference. हेलो आवाज आपने ऑफ किया हुआ है. हेलो अभी थोड़ा अंतर है. आप लोग चाय पी के एनर्जेटिक हो गए हैं. मैडम ने मुझे खाना खिला दिया है तो मैं थोड़ा लेजी हो गया हूँ. बट एनी सो I will quickly you can go through this because there are few things I want to show and which actually happening today around. Okay, that's the most important part. So in your nowadays we are managing. Okay, what happens if you work in Himalayas and what happens if you work in Rajasthan in the desert? Okay, extreme temperatures, right? One place you get 50 degrees, and if you operate your laptop or your desktop, the temperature also reaches pretty high. Your machine cannot convert. So low temperatures are not a problem, but high temperatures are big problem. Okay. One thing, basic physics question: what happens if I reduce the temperature? Okay, environmental temperature. Okay, uh, well below, well below, we can say 0 degree. I give you an extreme scenario. I go to moon, then in daytime the temperature is 200 degrees, and I go to moon where the place in the night the same thing, the dark side of the moon we can call it also, where the temperature is minus 200 degrees. Uh, what will happen at minus 200 degrees? Whether your circuits work or not. The circuit superconducting compare. Circuit do not work at those temperatures, right? Your semiconductors start behaving like an insulator. Semiconductor नहीं रहता. Okay, that's a big problem. That's why the temperature range is there. So below and high, both are important. Okay, that is why when people actually say, yeah, we will work at a very critical temperature zone, they really have to maintain that thing. Okay, you don't have to go to the moon actually, right? Recently, one of the things happened, right? You know, there was the Titanic, the remains of the Titanic, right? There is a company actually which takes you in a submarine to that place. I said, like a tourism, one accident happened. And the company CEO, one Japanese, one Pakistan origin businessman living in UK with his son, and 4 people died on board. They did not predict it out. Their temperature sensor did not actually happen. That was something people speculated. Uh, we have terrace changes, like here temperature changes. Sea well also temperature changes. So because of that, the cyclic certain system could not be triggered. Okay, now it become very much like uh, they become idle, and which actually you can say expose the submarine for the extreme pressure, and everything happened. People say thing did not happen. If you go to the sea bed, right, down sea bed, the deepest part, marine drive, the temperature also is used. Circuit do not work there. Okay, so this is just a basic physics thing. So in order to keep the circuit working the same state, we people have a temperature sensor there in the packaging itself. This temperature sensor, okay, we have on the in the package or on the die. नहीं आज नहीं है फिक्स नहीं है तो मुझे फोन करके बोला था मैं सिटी आया था बोल दिया ओके यू जस्ट कीप ट्रैक ना विद सम ऑफ द टीएस आई विल टॉक आई विल पास यू द नंबर आई विल टॉक है ना आई कॉल यू लेटर राइट सो दिस इज ऑल देयर so we have to have the temperature sensor if you just open this laptop you can find out what is the temperature of the chip you know you can track it if the temperature goes beyond certain thing then it will drop. So this is the temperature sensor which we people used to have it. Okay, and this is the way the temperature sensor society is for real. Power distribution network function. This is I will little bit take quick on this. Okay, once upon a time. Okay, I finished my BTech in '98. Okay, at that time there used to be one processor, one computer, one processor. Fast forwarding 2 3 years. There will be one processor, one computer. Okay, one computer, one processor, but very fast processor. Then fast forward again, then people realize that increasing the circuit frequency or making a faster processor is not a good thing because power is very much proportional to this VDD square. Okay, so and there is some component. This is CL VDD square. Some frequency component is here. Okay, a faster processor means frequency is high and the power dissipation is high. Okay, so they say instead of this precisely, these people have a better way of saying ki fine, we split. Okay, the compute. Okay, means instead of very heavy processor, very high speed processor, we can have two low speed processor. Okay, right? And because of that precisely, the power dissipation reduces. Okay, and something we do the parallel. For example, when I do the web surfing, okay, I can also do the printing parallel. So a lot of operating system level work we can parallel. That is why the multi-core processors came into the existence. And when the multi-core processor came into the existence, now then there is something more happen. Okay, so this was there earlier also, so it's power distribution network and all, but then the things changed. Okay, so it is something like on a chip. Okay, this is something like on a chip we are having a small processor. This is just for your you can say kind of this is a bus. That's this is the memory which I say. Okay, everything is connected to this kind of buses are there. So this is just for the depiction. This is not the exact thing. Okay, this is just for the elaboration. So here, let's say in a lab I have 8 processors connected to a network. I miniaturize them and put it within a chip. Okay, so network on the chip came. Right. At the same time, when I have to put so many things, okay, right, I have to scale down the technology node also because I want faster as well. Okay, so this precisely the technology node also drops down. Number of cores, you can say computing cores increased, and because of that precisely, number of matrix layers increased. But one more thing happened. The number of transistors in a chip actually grew. And every transistor needs to operate in a very simple, very correct manner. That's the thing. So, like in a city, we have the power distribution network, or in a lab, when all the processors connected to the power supply separately, that power supply also got miniaturized, okay, and put within the chip, and that actually is called the power distribution network. It is the same thing. It's a different area also. You can look at papers which are there on the web. Okay. So this is precisely there. So it carries a current from the patch to the transistor on the chip. It maintains stable voltage with the low noise, provide average and the peak power demand, provide current return path for the signals, and the avoid electromagnetic self-heating wear out, consume little chip area and wire, easy to lay out. So this is the a new area came for the power distribution network. So when we design the chip, one new thing added for the power profiling. Okay, and this is huge. Those who are having the physics or the maths enthusiast, for them, this is equivalent to solve a very large static circuit having billions of the resistances, millions of the current sources, and all. And we can say millions of the voltage sources. That is really challenging. Many people still are trying for this. Even we, two of my PhD students graduated in power distribution network design. Okay, so this is all there. So there are so many things for there. So ultimately, so we have the, you can say the ultimately VDD nominalization group is here. IR drop I have already shown you, right? Resistance drop due to that, and the LDR by DT noise. So I skip this precisely because this is something like which is also when we design, okay, when we packaging and all, this LDR power drop and LDR by DT noise also we have to do. And this is something is the packaging which actually I want to take you. So power comes from the regulator of the system board package and parasitic RF bypass capacitor help stabilize the supply voltage, but capacitor also has parasitic RF. Okay, so this is precisely my entire thing. This is a voltage regulator, this is a PCB place, this is a package in the pin precisely. Everywhere you see, you are adding resistances, inductances, capacitances. Okay. And due to the soldering, you also add certain resistance and the inductance. And this is the on-chip capacitor. Okay. And everything on-chip current demand, everything is there. And this precisely is so-called my complete packaging. How to reduce? Okay, if I have more number of pins, then what kind of packaging I should choose? Okay, right. But the more number of pins, that particular chip is working for a very high speed application. Okay, then how should I do the heat removal? Then what kind of extra layers I need to integrate? My chip will be exposing to the high temperature. Then what else I have to do? This is a part of the packaging studies. Packaging itself is an open area. Okay, so this part is there. So this is something actually we do, but I think now I take you to the long distance. I just leave this part because this is not required. Okay, this is little bit more to the design thing. Before I go forward, okay, I want to show you something. This is a paper actually I got in my today's mail. Okay, and it was there, 10th January. You see this, right? Are you seeing this? So now what is this? Okay, this is three-dimensional. Okay, MOSFET technology. What we have it here? We are having the 3D logic. Okay, it is connected with the storage. Okay, and this is actually connected with precisely with the sensor, and this is connected with precisely my. Okay, so this can be your small, okay, power source, and this is the future. And this we are going to have. This is today, some to 10th January. Today, it's US 10th January or 11th January here. So this is there. And this is something actually I just want to show you. So whatever we are doing, this is we have to do the packaging, everything, designing. Okay. There's 3D integration, 2D facts of this, everything we have to do like this. But here, I'm just taking, I'm thankful to Dr. Sumana Rao, actually who has shared the slides with me. Okay, being the part of one of the national level types. को पुलिस स्क्रीन चेक करो क्या था ओके so this is actually one of the part professor Tumara R Rao or Tumara is an advisor in this India semiconductor mission and he is the pioneer researcher in the area of packaging. He is from Georgia Tech, so something precisely he shared. Okay, so with me, and this is something this this is something precisely he has done. So today's world, when we are going for this packaging, people are doing glass for the packaging. Okay, and one so this is like the characteristic precisely when your people are going for the glass packaging. The characteristic which they are choosing, the electrical is a high resistivity, low loss and low RDL. This is a redistribution layer is there. I will show you one redistribution layer where it refilled is actually. Physical smooth surface finish, large area availability, and is ultra thin can be. This can be thermal high conductivity it can offer. This is high modules it can offer. The low warpage can be a resistant to process chemicals. TPV and RDM for low cost via formation and metallization. This is has high reliability compared to which is matching to the silicon and the PWB. And the cost precisely is okay at it's very less this year. When we talk about the different materials for this for the packaging, okay, like silicon carbide based and the silicon is a polysilicon, organic, metal, ceramic, glass actually fulfills more or less and all the in precisely it actually fulfills all kind of criteria. Okay, so next generation beyond SI, beyond packaging, overcoming shortcoming for the improved performance, cost, reliability, and the miniaturization. These four things are there for which actually we people are looking for the advanced packaging methods. Okay. So when we talk about the silicon package, okay, material is highly electrical. Electrical losses are very high. Okay, it offers high relative constant as well. And precisely interconnect which are there, they are also offer the high RNCs. We use polysilicon instead of metal. It has very, you can say greater, you can say connect with the actual silicon there. Process also is very much defined. It also reduces the process cost as well. Okay. So this particularly, when we talk about the interconnection or so this silicon actually offers even the high RNCs compared to other materials and all. Okay. And the cost is high. Okay, due to the small micro size for the large packages. Okay, right? But manufacturing infrastructure exists and it provides the highest RU density. That is the reason specifically we are doing. I will share all the slides, whatever I have done there and what I am doing today to Rashi Madam. So she will pass to you, no problem. Okay. So when we say how to precisely do this thing, this is the actual fab is there. Has anyone of you visited any fab? Mr. Achin Jadana will be coming here. Okay, he is a very good friend of mine, and he was with a group head in semiconductor lab Chandigarh. He will show you a lot of things. Okay, so I leave this portion for him only. Apur, what time is now? 4:50. Okay, I have to show something to you in next half an hour. Okay, then precisely I will stop by 4:45. I have 6 o'clock class, so I have to reach and prepare for that as well. So this is precisely there. So Jadana sir will actually tell you. So this is precisely you can say there are multiple packaging platforms out there, multiple equipments out there precisely. Okay, and if you just look at it, we are having the advanced you can say plating line is there, high speed ECB bonders are there. Okay, and the reliability testing equipments are there. 1997, I did my internship at L&T Mysore. So L&T Mysore, when I did the internship, it was really very much, you can say, it was a new experience. I was 19-year-old kid at that time, and these people show me the way the actually PCB fabrication happens. those who have done their undergraduate with me at the time, they might be knowing the downfall of the ITI, Indian Telecom Industry, and the rising of the vendors like the Airtel and all. Okay, there was if this is getting recorded, I will not say many things. And many newspaper articles from there, you can still look at it, it's there and there. We guys were very much what we can say as reliant actually. Uh, we were very much self-reliant in this PCB fabrication, PCB design, fabrication, and packaging and all. I've seen this entire thing. So what these people do, let's say this is my entire PCB is there. They have to collect the component, okay, and they just dip this entire PCB, okay, at the lower part in the molten bonded material. Okay, it used to be there, and only in the tips it used to just get it, not anywhere else. Okay. Just because of capillary action, it's very fine thing used to happen. So we lost everything. Somehow we are currently not producing any, you can say, office kind of phones which used to have the recording facility. You might have seen our offices. We are having this recording phones for, we can say, call forwarding everything. So I'm saying you with many of you can see. It's still these I think, but you used to manufacture complete thing in the country except the chip part. Jatana is coming tomorrow. No, day after. Tomorrow day after. Tomorrow is coming. 13th he has a session, right? 13th we have a session. So he will tell you, ask him where we were in chip manufacturing and where are we now in chip manufacturing. I'm not carrying, okay, I'm not carrying that particular the photograph. Okay, it's in my mobile. I can forward it. I will forward it to Apur. Apur, you can forward it to everybody. So when I saw that thing in 2014, okay, it was comparison between India and China, and I can draw it here. It was like the billions of dollars. Okay, and that's India China. China was something like this, and India was something like this. This is a timeline. When I saw false, I saw only 1 gram. I said, where is India? And we were here. But then, 2014 till 2023, our graph is more or less increasing like this. It is constant, but increasing. We are not at zero anymore. Okay. So that is why, okay, and when we talk about manufacturing, circuit we are designing, fab someday will come. Okay. And but the actual demand we have to generate. That is why I am saying setting a fab is a $5 billion to $15 billion business. Okay, right. And it is like having not a white elephant, it is having a white whale. The pool with a pond of white whales at your end. If you really want to earn profit, we have to generate demand. And if you think only IT will generate demand, so this will be a dream. Even if BSc engineering, BSc physics, BSc math, okay, those who are BSc electronics, those who are doing this, the demand will be generated by them also. And we are working towards that. And because I am leading one national initiative which targets even these colleges. How to train a BSc electronics, okay, BSc physics person to design a circuit during their own BSc MSc studies as well. We are working for that. We are that initiative is started, we can say some 2 3 months back. Okay, and we are leading that thing. And that will be the game changer in future. So here precisely we have a lot of this is something which is most we can say advanced things are there, the 5 micrometer lines out there and so on. Okay. So what are technology barriers? Thin glass panel handling, okay, board formation, how to do, okay, thin and the low K directly you can say reduce the layer precisely we have to put, okay, grass crack when dicing, when I cut the this grass may crack, okay, you can try, if somebody want to try, I tried this thing, okay, when it talks to Professor Tomala, he said, try cutting a glass in a perfect hexagonal shape. With whatever is there with IIT, me and one of my colleagues in mechanical, we tried and give some time to this. It happened really last year actually. Okay, and it perfectly went with mechanical. So perfect glass cutting, hexagonal. Try. Okay, it's tough. Okay, IC board assembly. There are so many things out there precisely. Okay. Oops, I promised you to show you the wafers, right? I forgot. And maybe next meeting whenever I meet, I will show you. Okay, so wafer will look like this. This is my silver wafer is here. Okay, right. So this is something this precisely what you say when we have to showcase small wires are there and all how to do this. I think I skip. This is you can see this is the PCB. This is my you can say my connectors are there. Okay. This is my you can say substrate is there. This precisely is my RDA layer is there. And again precisely one you can say inter this one is there. And then precisely my chips are there. You see so many right? This interconnect is getting connected to this one is getting connected to this one, and this one is getting connected to this one, and this is my output pins out here. And I have to, you can say, make this, when I say this particular chip is there, okay, the size of the actual chip, the size of the actual silicon is very small. My thumbnail size, this is the size of Core i7 processor on the silicon, this much only. But Core i7 processor is this. Because there are multiple levels out there. Very fine pins you have to take out and you have to connect. And here you remember yesterday I told you materials you really have to choose carefully. Those who are working in physics or chemistry domain or chemistry type domain, uh, we will be actually we are soon going to launch one 3 month course in the like material analysis using quantum espresso and quantum wise. I think some of you might be knowing Professor Ishankur Sakia, Guwahati University, he's in material science department. His PhD student worked with me and he's like working at our end also. And we have submitted 3 4 papers recently. And we have explored different material properties and all, and their usage in designing the next generation devices also. Okay. So those who are working in the physics domain who have a love for the physics and this, you don't have to precisely buy very costly software. Freely available, open source software also you can do this. And a 3 months course we are doing. The course will be online. Okay, it will be running online by IIT Guwahati. You can register. And you know what is the best part of this course? This is free. Okay, but your certification is costly. Means if you really want to get a certified something like this, you really have to pay. But you can always encourage a student to do that. Okay, that will give them. And why I'm telling you, that is why I was asking from the first thing. Hey, what is specifically the most recent you can say government of India objective? 6G and all that is fine. But how do we do the 6G without the electrical system design and manufacturing? That is something. So if your students have good knowledge of device design, They have a better prospect in the industry. Companies are not looking for IITs all the time. They will start looking for the right talent pool. It is right talent pool. It may come from Guwahati University, it can come from AEC, it can come from let's say Jalukbari University, or it can come from IT work. It doesn't matter. Person must have the right kind of knowledge. And for that, a person need not to finish the studies first and then go for that. It can be done along with the studies, and that's a better way of doing it. Please encourage your students because this is something we want at this particular level, okay, and we have to ultimately we have to go precisely at a very different level itself. So ultra package means GPU and HBM on the same. It means there are multiple functionalities on the same die. Okay, now the CPU, GPU has got the same panel. There are multiple things at the same time. That is why I have shown you that three-tiered or four-tiered picture, right? Now, you remember, yes, that day I was talking about you can say, this TFET based, vertical TFET based biosensor, VTFET, which Parvita is working. Okay, she has got fantastic results. But one of the challenge I got how to compete where to sorry, how to fabricate and where to fabricate. Finally, once one of my US counterpart he came with that and he told me that he will fabricate. I don't we India don't have the facility for vertical defect fabrication. So we are getting it fabricated from outside, we are giving the other person also co-authorship. But yes, we are actually generating something worthwhile. Okay. At the same place, at the same die, we want at the same silicon, same silicon area, we want the compute, we want the memory, we want the sensors, and we want everything out there. Density is going to grow a lot because our desires are really a lot. Okay. And this is something which will happen with the help of we can say advancement in the semiconductor technology itself. Okay. So I would say this is just a characteristic part I noticed. So you can see precisely this, this Professor Rao, because the research lab, done a lot of many things. They developed one micrometer panel ideal. Okay, this is the pictures of that. This is the kind of thing precisely he has done at this place. The laser, they are using lasers basically to drill the holes. Okay, only Israel is not using lasers to shoot the incoming missiles. People are using lasers to drill the holes also in the small scale PCBs. Okay, and why laser? Confined source of energy. Okay, symmetrical, repetitive. Okay, and with less damage. Okay, so that's why we are doing. So ultimately, when we say the IO pitch and the wafer foundation glass packaging itself is fulfilling all the criteria and all. R&D innovation in glass packaging, you can. This is there are a lot of things out there. The cost, I've said it there precisely. I'm going to say cost is less. Okay, IO pitch is less. Okay, thickness precisely is not the lower water thickness is not that much required. It supports high frequency performance. Okay, like simple like RDL it is supporting, reliability is high, thermal management is better, 3D integration with two glass vias are easy. That's what I've shown you that major case. And this is going to be the game changer. So this is precisely there. This is the work done by Professor Rao. Things I think there are so many things out there, but I think I will skip this because more or less this also has a GT. So when I did like people nickname me as GT actually. Like I say, we also have a GT here, so he used to make it fun of me because of this GT. GT stands for Georgia Tech there. Yeah, this is there. This is because 3D with the TSVs are there. TSV is through silicon via for the 3D printing is there. So the Georgia Tech 3D camera radar module they have kind of done everything. But something very interesting, I think I just stop it here with this, and not with the presentation and all. One final thing that I did, I want to show you this make it this way. Chiplets. This is precisely the company. Okay. This slides are also here provided by Professor Rao. Thanks to Brian Black as the CEO of this for sharing the slides to us. Okay. And making this presentation very intuitive in terms of the knowledge. Meeting future performance demands through glass packaging. That is something, is a most recent one in one of the talk precisely he has given. Okay. So specifically, chiplets, what is chiplets are, is a design methodology for disaggregating associates into multiple types. What we have done, I will give you an example of a chiplet. I was not knowing also up to 3 years back. AMD, I really appreciate this company for bringing the real innovations. It was not Intel which came with the multi-core processor idea. It was not Intel which started using the copper interconnects. It was the AMD which started this idea. Okay. Some years back, I heard, because actually I work in supercomputing also, so my heart lies also there. So that's the thing. So I follow a lot of things. And so this is one of the things precisely I was following. And I found, hey, AMD released 64 core processor. I said, wow. I asked my friend, what is this? In fact, my friend, those is some, this part will delete. I'm going to say something. Yeah. Okay. Somebody's number I'm sharing is not good. Okay. So this 64th chip, I say, how did you do this? He asked me, think. All mine. So they actually made four 16 core processors. They pasted on the silicon die, four different dies, they pasted and they made, okay, those things. That it is a metallization over those. They were the chiplets. That is a chiplet processor. IT what we have 48 core processor. Okay, systems are there. Okay, my lab we are actually seeing we have everything right from the atom to the chip tape out we can do. Okay, that is why I'm always inviting you. Hey, if you have something to do together with us, you are always welcome. Okay, so chiplet is design methodology for disaggregating associates means earlier we want everything into the same thing. System onto a chip. But now we are saying, hey, segregate the functionality. Because one functionality may need different kind of even the fabrication. Okay, and that precisely is the right point. We say not all the fingers of a hand are equal. The same rule is now applied to the chip design also. The chiplet is a substrate vendor that makes it easier. This is a company which is making this multiple associate dies out there. Okay, so the CPU and the transistor is scaling. If you just look at it, okay, 4004, which I told you the Intel processor came to the Intel Haswell. Okay, right. This is huge. If you look at number of scaling part there in this, okay, and AMD on AU, okay, they are almost at the same level. Okay, I am leaving this part here. Design cost is troublesome. Okay, advanced design cost precisely 16 nanometer, $106 million. 5 nanometer is approximately the 5 times, and this is okay. Is very you can say important. Okay, IP qualification, architecture design, verification, physical design, software development, prototyping, again validation. Okay, takes really a huge cost. This is precisely the thing. If you just look at it, circuit designing, physical and architectural labor, right? They don't take much time. The time it takes the verification, and second time it takes the software to write. When you look at the supercomputer, any processor computer performance, they will say this is 5 gigahertz processor. You never get 5 gigahertz equivalent performance. Our software, we are not writing up to a level which actually harness the complete power of the underlying hardware. So supercomputer, we always say we have a 5 petaflop machine, but that 5 petaflop is the peak performance. Here flop is means FLOP. We always say कि ये flop हो गया, but वो flop नहीं है. It is a floating point operation actually. I'm talking about. If I multiply 2.325678 with 10.12345678, how much the result will be, how much accurate it out, how far I can do. So in 1 second, how many such operations I can do, that defines the flock count. If I am doing millions of flops floating point operations per second, then the hardware is very much equivalent for the Dyson category of the megaflops, gigaflops, teraflops, petaflops, and now Japan has developed world's first exascale or the exaflop computation. Mine means 1 second 10 to the power 18 computations are going on. Look at this, all this information is there on the app. I'm not saying anything. Okay, so this part, the cycle is there. So performance scaling is something like traditional transistor scaling is not working any longer. So twice 2x transistor parameter square, we are putting half power, power is half, okay, and all those things are there. But scaling, I'm to say when we talk about the today different. The more die area to increase the performance, more power input to turn on the additional die area, and more IO bandwidth to, you can say, feed the beast, whatever we call it precisely, and leading to the micro architecture to find more performance, and something is there. So here precisely we are moving from the new reality in green. Now the AI is there. This is driving. Okay, right, but specifically it will take really a lot of time. But when we talk about the packaging, the system is integrating into the substrate, that is there, associate disaggregating into the substrate, and there are lies of lot of dies in the substrate is there. This is why substrate is there, and you have a lot of dies you can see. Now this everything I have to package. And you know what is this? When people say, hey, we are doing this. Okay, I was in the presentation and I said this is no different. Memory, right? In supercomputers, this is the advantage of me working in the CS domains. I'm going to say huge memory, terabytes, I say petabytes of memory. How do you store? You can imagine there is a system of I have the hundreds computers here, servers. Each server has two processors. So I have 200 processors. Okay, and now I have to store, let's say, 10 petabyte of memory. How do I store the 10 petabyte of memory? Anybody? Anybody? I cannot do it in a system, right? Every system has a limitation. 32-bit processor can store up to 4 GB. Can support 4 GB of the RAM, for example. Virtual disk can be of anything. But how much big disk I support, na? So what people do, they say, I built, okay, a very high speed interconnect, and I have an external memory bank, which is again a high speed memory, and I connect this, and this is the mini size of the knob. They got inspired by the supercomputing thing, and they said we break the functionalities, put it over the same die, okay, substrate shall bond it out, and then we do. And the performance has improved actually through this. Power management become more easier. Okay, so all these things are there. Okay, so ultimately there are some challenges out there. How the die to partition, how to communicate, how to power this for the die, and how to clock the die, and how the security provided. There are few challenges out there precisely. This is all about it, and a new subject are needed to make this thing actually possible. And why this is required? The let's say this is a green icon, I call it the green. Okay, right? This green one, I want to fabricate a 65 nanometer, but all this you can say the brown ones I am fabricating at 5 nanometer. This green is my sensor. Now there is a common clock which is running. How to you can say do the clock distribution? I didn't cover the clock distribution. It would have taken longer time, but this is all there. So this is something something big challenging is there. Okay, but I think this is something I will the packaging die and all what people will actually use it precisely. I just give you one particular picture and I will stop it here. So the solution what they are providing, okay, like they provide a tiny RDF, tiny vias are there, okay, they have the extra integrated components are here, they have the BGS are there, the micro bumps are there, and there is PCB they are solving it. There are multiple ways people are doing this, glass and the white glass, we already seen it. So I stop it here, okay. So ultimately, there was about different mechanisms. When the system was there, this was the bridging was this, vapor level, echo was there and all. But ultimately, when we have to attack it, this is precisely the problem which we have to face and solve. So with the increasing complexity, right? With the increasing everything, okay, right? The packaging industry is nurturing up to this level, it's migrating to this levels. And from where this will come, I have given the sensor thing. Uh, I have a mobile, all of you have mobile, right? Okay. Uh, when you're clicking the picture, right? Okay. So only that portion need to work. When you're listening the music, okay, right? Only that portion must work. There should be the minimal OS working at the same time. Only those kind of apps are working. This is the way your system performance will be longer, better, okay, and more reliable. That is why the software stack was built. How to enable this? And this is the reason software engineer jobs will never die, even if the AI comes into the place. So with this, I stop it. I have 5 minutes, maybe 10 minutes to answer your questions if you have. So if you summarize, we start with the resistance and we ended here. So good, and no questions. Then this, I just thank all of you. It will be a long day for you, okay? And I know it's very difficult for a person to sit in such a long interactive sessions. I myself attended one course of Professor Umesh Mishra when he was visiting IIT Delhi. So there was no a